So let's start. So last time we began talking about complex Jacobian elliptic functions. Actually, in February, I guess, we defined Sn as the inverse function of the elliptic integral of the first kind, like this. And also we introduced a complex Sn probably 1 month ago by using the inverse of the Abel-Jacobi map. But we discussed that any elliptic functions can be expressed as a ratio of theta functions. It's true that rational functions, but yeah, better to say it's a ratio of theta functions. So, or Sn or Jacobi, the elliptic functions should be expressed as ratios of thetas. So,
where is the K? Ah, sorry, K is written here. Yeah, I see.
Yeah.
K is written there. And K, you said K can be complex. Is that what you said?
Yeah, right.
Yeah. Okay.
K is a function of tau, and this is a shorthand notation of zero value of thetas. Well, maybe I should add.
No, that is okay. It is written below. I already noticed that. Yeah. It's okay. I just didn't notice the K.
So the answer is like this. And well, yeah, we were checking that they really coincide with the former definitions. Mm-hmm. And their ellipticity or periodicity can be checked easily by using the case periodicity of theta functions. For example, theta 1,1 and theta 0,1 have period 2. So this function is periodic in the direction of 2 pi theta 0 squared. Similarly, it has another period, this, which comes from the periodicity of thetas. And so, as thetas are entire functions, the ratio is, of course, meromorphic. So this is an elliptic function. Similarly, Cn and Dn defined by this formulae are elliptic functions. Fine. And yeah, and their periods of Cn and Dn. And yeah, we have checked several facts, properties. For example, Sn is 0 here because theta 1,1 odd theta function is 0 at 0. Similarly, Cn and Dn are 1 here because, well, by definition, it's clear. If v or u is 0, then yeah, the numerator and the denominator cancel. And yeah, oddness and evenness are also clear. This is odd and other thetas are even. So for Sn is an odd function, while Cn and Tn are even. And yeah, these formulae were used as definitions of Cn and Dn when we were considering those functions as real functions on the real line. But these formulae can be proved using these definitions because we have many additional formulae and other useful formulae.
Takashi, the trigonometric case is the limit when k is what is 0.
Yes, that's okay. What I'm going to talk.
No, just a simple question.
Yeah.
Okay. Mm-hmm.
Hello.
Hi, there you are. You have your new.
Yeah.
Yes.
So and yeah, these formulae are consequences of addition formulae of theta functions, and we have proved that derivative of Sn is the product of Cn and Dn, also by using addition formula. And also Jacobi's derivative formula. And so yeah, we have proven that Sn satisfies this differential equation, which means that Sn is an inverse function of this elliptic integral. So we have come back to the first definition of the Jacobi function. Well, yeah, I have cheated a little bit. First, of course, this formula, or yeah, this formula should be considered on the Riemann surface. So, and we need to specify the contour which connects 0 and Sn of u. So first, yeah, we'd better consider only neighborhoods, small neighborhoods of 0. And then there is no difficulty to consider such an integral. And then, so since this expression is analytic, I mean holomorphic in U, we can analytically continue everything. one problem. The other problem is, so this notation. We have our defined Sn of u by this formula, in this section. And K is defined by this. So here, there is no K on the right-hand side. So a priori, it should be denoted by such notation. It really depends on u here and tau. Actually, tau sits here, and everywhere. But because of this expression, when K defined by this formula at tau and tau prime as the same, then this function is the same, is defined uniquely. And so that's why we can denote this ratio as a function of K. So that is Sn. That's some comments to the last week's talk. Okay.
Okay.
Now, let's check other properties of Sn, which we have already shown over R. Well, Sn is doubly periodic, as we have seen, but over R, it has a period 4K. K is the complete elliptic integral of the first kind. Well, what we have shown is that the Sn has some complicated pairs. And well, yeah, as Jan has mentioned, Sn converges to sign when k goes to 0. And well, yeah, we have proved addition formula probably in March or in April. No, in March. By just differentiating, well, yeah, by checking that if this is constant, this side is also constant. So let's check these properties by using theta function, properties of theta functions. So yeah, well, actually, we have some time, maybe, but well, yeah. This slide was made 2 years ago, or well, yeah, 2 years ago or 4 years ago, and so at that time we didn't have much time. But probably today I can talk a little bit more detail. Okay, so we have proved these are the first addition from the limits, and then if we have time, I'll check the periodicity. So what we want to prove is Sn u plus v is equal to this one. And what is this? This is, yeah, by definition, this one. And this can be a well, it's too messy, so let me omit writing explicitly. But as you know, this is something like this. This is like theta 1, 0, 0. So essentially, if we multiply denominators of the numerator of this expression, we have ratio of or some complicated polynomials of theta function.
Takashi, these
Yes.
arguments should be x and y, I think. In the arguments
so
on the bottom line, the red line that you added by hand.
yeah,
The bottom line.
Yeah. This is.
I'm just checking that I'm following because it's a bit complicated for me. So it's, yeah. Thanks. Yeah, I know it's not important, but I just want to see that I'm following because it's complicated. Okay.
So, well, yeah. So this equation actually comes from the ratio of two addition formula, which were named A3 and A2 2 weeks ago. So one is this, and the other is this. So the ratio of them, for example, this theta 1 cancels, and from here comes this expression. Similarly, the ratio of them are equal to this expression. So addition formula is direct consequence of properties of theta functions we proved before. Well, okay, that's easy. The other property, for example, Sn converges to sine when k goes to 0. Let's check this one. Well, actually, since we defined Sn by theta 1 u v tau over theta 0 1, essentially like this, and the k is yeah, this one, theta 1 0 over 0. We need to know what limit of tau we should take, and this is the answer. In fact, for example, theta 0 0 of 0 tau is equal to En squared and when tau imaginary of tau, exactly speaking, yeah, in tau goes to plus infinity, this is the limit. Each term in this series has absolute value . like this. So if imaginary part of tau gets larger, then this goes to 0, unless n is 0. So if n is not 0, then this exponent goes to minus infinity, so it is 0. So it is, yeah, this converges to 1 when tau goes to, yeah, let me write this way. And theta 1, 0 of tau is exponentially so this is not true. Sorry, this is it. And this is something like this. So when n is 0 here, n is minus 1 here, n is 1 like this, and so on. So by the same argument, it goes to 0 when goes to I infinity. So what we have to show is when tau, or imaginary part of tau diverges to plus infinity, then Sn defined by this goes to, well, just a moment. Yes, okay. Minus. Well, in this limit, this expression goes to sine of u. How can we show that? Actually, what is theta 1? This is and when yeah, n is equal to 0, then yeah, for simplicity, let me use this notation. So this is when n is equal to 0, so this gives this, and from this expression we have since this is 1 over 2, when n is equal to 0, then this is 1 over 2. And when n is equal to -1, oh, this part is also q to 1 over 4, and this part becomes something like this. And when n is equal to 1, then here comes something like this. And yeah, similarly, we have on the other hand, oh, this one, well, yeah, this is it. And by the same argument, or it's this is when n is equal to 0. So when tau or imaginary tau goes to plus infinity, q converges to 0, and this part converges faster than this. And so, as we have seen, theta 0, 0 goes to 1. And theta 1, 0 goes to q. 1 over 4. So, yeah. This is this, so this. The leading term is this. Leading term of this part is this. Leading part of this is this one, and leading term of this is this one. So as a consequence, it is minus here and 1 over 4 over 4 and so finally we have so sin of x is equal to 2i by this Euler's formula. We have sin v to pi v, and this is equal to sine of u, because v is defined by this is p. And we know that this goes to 1. So it goes to 1. Oh, sorry, u, which means this one. Okay?
It should be 2 times sine.
2 times?
Yeah, it should be 2 sine u, 2 times.
Yeah. So something is wrong.
Okay, so modulo a lost factor of 2. I mean, it's not a...
Yeah. Yes, this one is twice, sorry.
Mm-hmm. Okay.
Let's check. Theta 1, 0 is this. And when n is 0, this is Q 1 over 4. When n is minus 1, it's also, and when n is 1, it's and so on. So this is equal to So the leading term is twice q to the power 4. So this is it. Thank you. So therefore, Sn converges to sign. And we also discussed the limit when k goes to 1. And well, yeah, actually, this was a homework assignment. That limit of Sn when k goes to 1 is a hyperbolic tangent. Well, this is proved by similar, not similar, yeah. This is proved by means of Jacobi's imaginary scenario.
After you have already proved the formula for differential, after you already prove that, then you have the integral representation, and you can just take k equals 1 in the integral.
Oh, well, yeah, yes.
Then it is probably easier. Also, certainly for the case of sine, this is the easiest way to prove it.
Thank you. Yes.
No.
Well, yeah, I want to prove those.
You want to prove it direct.
Properties, starting from properties of thetas.
Yeah, understand.
Yeah.
No, that's
actually that's
the derivative property for the thetas. You already proved that relation.
Yeah, yes, right. So from this, yes, yeah, we can take limit k goes to 1, and then it can be easily integrated. Another proof is related to some deep properties of theta function, modular transformation, or Jacobi's imaginary transformation. Which relates such theta function with modulus tau. In fact, for example, theta 0, 0 is almost the original theta with some correction. It 0, 1 has same correction factor, and here we have 1, 0. So, well, we can prove such properties by starting the definition and using the comparing case periodicity. And location of zeros. Using this, roughly speaking, this goes to theta 1, 1, or with some constants. This goes to theta 1, 0. And so Sn of U with this modulus is equal to this. As you know, this is Sn is ratio theta 1, 1 over theta 0, 1. This is theta 1, 0 over theta 0, 1 with some constants. So this corresponds to this. This corresponds to this. And this factor cancels. So when this goes to 1. Actually, this is equal to this, or exactly speaking, which can be proved by, again, by addition formula. So it also was, and this is and by some limit of addition formula, we can prove that for fourth power of theta 1, 0 plus fourth power of theta 0, 1 equal to fourth power of theta 0, 0. So as you remember, addition formula have special forms. Sum of products of 4 thetas is equal to product of 4 thetas. And our some specialization gives you this one. So this k goes to 1 when this k goes to 0. And we know that if Sn goes to, k goes to 0 here, then it gives you a sine of I. And this gives sine of I. And this is almost I of hyperbolic sine u. This is equal to hyperbolic cosine u. So as a consequence, this is hyperbolic tangent. Okay? Two. So, yeah, this is another proof of this limit. Oh. The periodicity is a little bit more complicated. Yeah, so we know that SN has periods, two periods. One is twice theta 0 squared. The other is pi tau theta 0 squared, which we proved last time. And we want to prove that this is actually 4k, okay, in the elliptic, complete elliptic integral. Well, yeah, we have already proved that A periods and B periods of this elliptic integral is equal to 4 of k and 2I times k prime. Yeah. So, they are periods of inverse function of this integral. So this is periods of Sn. So we have two expressions. One of expression of periods is linear combination of them. The other is linear combination of them. So at least we know that the lattice is generated by them, and by them I equal. Namely, 4 of k, large k, is an integral linear combination of them. 2i of 2i times large k prime is linear combination, another linear combination of them. Well, actually, they are more simple. First, yeah, so sorry. We have still some time. So I can explain more detail. Just a moment. It's equal to this was what we obtained by the some rough argument. But well, when tau is purely imaginary number, then by using definitions, for example, this one is equal to e minus pi n squared t, which means that this is real. So pi is real, m1 is an integer, real, and this is imaginary. On the other hand, this is real because k is this, and by the same argument, it was e pi I. This, so this is also positive real number. So this side is a real number. This is real. So we cannot have this part, namely k is equal to this one. But if this is not one, if it's larger, well, yeah, m1 should be integer, and of course not 0 and positive, because this is a positive number and this is also positive. So m1 should be a positive integer. But if it is larger than 1, then we have such a inequality. But well, let's consider incomplete elliptic integral of the first kind. And well, since it's positive, so integrand is positive, it is increasing function, and when c goes to 1, this is k. And when c goes to 0, of course, it is 0. And so by the intermediate value theorem, am I right? or there is some number C prime where integral or this function is equal to this value. In other words, this is, and C prime is, as we say, strictly less than 1. But so by the definition, by the definition of SN in terms of theta functions, we have such an expression. This is what? 1/2. And we know that theta 01 of 1/2 is theta 0. So theta 1 of 1/2 is equal to minus theta 1. So this is equal to 1. 1 is strictly less than 1. That cannot be true. So what was wrong? This assumption was wrong. So k of k is expressed by theta function by this simple form. Therefore, we have this, from which we have this period, which we derived from the expression as an elliptic integral, is equal to this period, which we obtained from the expression as a ratio of theta functions. Well, this can be proved similarly, or we can use this modular transformation. So all properties we discussed in February or March can be derived from this definition of Jacobi's functions. So that's it. Any questions? Well,
You're going to answer that question of
yeah.
last week, no?
What? Oh, yeah, Miss Wu. So, yes, yeah. You asked me what is the inverse function of the second elliptic integral? Am I right?
Yes, yes, thank you.
Yeah. So actually, it is not a good function because if omega t is abelian differential of the second kind, or actually it can be third kind, then such function as a function of z, say it's, well, yeah, u of z, has poles if well, yeah, sorry. Yeah, first, let me consider abelian differential of the third kind. Then omega 3 has, for example, I'm somewhat confused. If omega 2 is a second abelian differential of the second kind, then we have such a pole. For example, if n is larger than 3, this is very bad because integral has such a double pole, triple pole, etc. So in the neighborhood of the pole, it is not one-to-one. So we cannot define the
inverse.
Yeah, yes, thank you. Inverse function, even locally. So this is not good. For the abelian differential of this third kind, we have such a pole, and we have logarithmic singularity, or at least some locally multiplied function. So it's also bad to consider inverse function of such function. And yeah, when omega 2, the second aberrant differential has a second order pole without residue. Then, yeah, it has such a behavior around the pole. So, yeah, sorry, what I was considering was wrong, but yeah, but anyway, for example, if omega 2 is standard or aberrant differential of the second kind, A period is this one, B period is some linear combination of this completing elliptic integral of the second kind and first kind. But then, well, it means that inverse function of this elliptic integral has periods E of k and some complicated function. So at least this function is not a function on the elliptic curve, on which this differential is defined. So, yeah, shortly speaking, this is a rather complicated problem.
So you generally we cannot express Z by omega. I mean that, so you mean that it doesn't exist the inverse functions of the second kind elliptic integrals.
So, sorry, I cannot hear you well.
So I mean, so it doesn't exist the inverse functions for the second kind of the. It does not exist the inverse function.
Takashi, she said the inverse function does not exist.
Yeah, yes.
I just tried to think. You can also write it for Takashi.
Yes. You mean this? Actually, in this case, we have second order pole, and therefore, we cannot rule out the existence of the inverse function by such arguments.
So Takashi, I'm just typing what she said. I think that is what you said, right? Question mark.
You mean chat?
Yeah, I just wrote it. Sorry.
Sorry. Yeah. I see. The reverse function does not exist for the elliptic interval of the second kind. Well, I cannot rule out the existence for
You said that.
such cases. I mean, second order pole.
The case n equals 2.
N is equal to 2, yes.
N equals 3 and above you can.
Yes, even locally, it does not have an inverse function because of this multipleness, or yeah, because this is not one-to-one. But in this case, yeah, I just realized that the integral has such a form, and it's at least it's not easy to prove that this cannot have an inverse function. But still, if it has, then it has periods like this. So it's not our old home. I mean, there this good old elliptic curve, but it has another period. So what should I do? I cannot say.
I'm just thinking the inverse function, if it exists, it's also periodic, right?
Yes, because of the structure of the elliptic curve.
If you take this case where very, very close to 0, this thing that you just checked, you said that u is very close to -1/z for z very close to 0.
Yeah.
So you can invert this very close to 0, and you see that z is very close to -1/u.
Yeah, yeah.
Z is very close to 0.
Yeah.
So we're looking for an elliptic function which is doubly periodic with this behavior at 0. And I think it's impossible, right? It cannot be. You cannot have a periodic. You cannot have a doubly periodic function with a simple, with a pole of order 1 at 0. Is it correct?
Perhaps that, well.
I thought this. I mean, you have to have at least you have to have a double ordered pole. That is where you get. I mean,
yeah.
So, you see what I mean? I'm looking at the middle of the page where you have is asymptotic to -1/z.
Yeah, yes.
So this relation can be inverted in a very, very, very small neighborhood of. So you get that z is -1/u.
Yes.
For a u very close to 0. But now, if you want it to be doubly periodic, you cannot have a doubly periodic function which has this behavior at 0. I think you proved that theorem. I mean, I've.
Doubly periodic function can have such poles, but at least two.
Just have another
I mean, yeah. Yeah, probably you're right. Well, yeah, if it has just one pole.
If it only has one pole, yeah. So the question is, does it?
Then it's yeah, such a doubly periodic function is prohibited. But still, yeah, well, Sorry, it's an open question.
Okay.
Anyway, that's all what I wanted to tell you about elliptic functions and elliptic integrals. And thank you for your attendance.
Mhm.
It seems that none of you need, I think, I mean, yeah, evaluation. So
No, nobody has to do the exam.
okay.
So thanks. Thank you.
Thank
See
you.
you sometime.
Yeah,
Yeah.
Thank you.
thank you. Okay, maybe
Please.
Takashi,
Yes.
you can just stop recording. No?
Yeah.
Yeah,
Can you-
yeah.